All right, let's just dive right into this explainer. Today, we're demystifying exactly how computers and mathematics use fuzzy relations to handle the messy, ambiguous reality of the real world. We hear a ton about fuzzy logic all the time, but today, we're popping the hood and looking at the absolute foundational math that actually makes the whole shebang work. Because this is a pretty mathematically dense topic, we've broken it down into a straightforward roadmap. We'll hit the matrix foundation, crisp versus fuzzy relations, operating on fuzzy relations, the art of composition, and finally, returning to reality with AlphaCuts. Let's get to it. Starting with Section 1, the matrix foundation, we're going to ground ourselves right out of the gate in something highly concrete, which is the basic rules of matrices. Why matrices, you ask? Well, because fuzzy relations are basically always represented mathematically as fuzzy matrices. They're literally the structural blueprints for everything we're about to talk about. So the absolute crucial point here is compatibility. You can't just take any two random data sets and mash them together. To multiply matrix A and matrix B, the number of columns in matrix A must exactly equal the number of rows in matrix B. It's like puzzle pieces. For example, if you have a 7 by 3 matrix and you want to multiply it by a 3 by 5 matrix, look at those inner dimensions, the 3's. They match. That works perfectly. And it's going to result in a brand new 7 by 5 matrix. But if you try to multiply a 6 by 5 matrix by a 3 by 6 matrix, the 5 and the 3 do not match. No way. That operation is completely undefined. And visualizing this brilliantly illustrates the mechanics behind it. The rows of the first matrix have to map directly, and I mean precisely, to the columns of the second matrix. The product is then calculated by multiplying those corresponding elements together and adding them all up. It is rigid, it's structured, and it's exact. Moving on to Section 2, crisp versus fuzzy relations. Now that we have our rigid mathematical blueprint, let's look at the philosophical and practical differences between strict logic and, well, infinite gray areas. See, in classical math, we deal with crisp relations. With a crisp relation, an ordered pair either completely belongs to a relationship or it absolutely doesn't. You are strictly a 0 or a 1. Think about drawing a hard line between an apple and a not apple. Simple, right? But wait, when you're halfway through eating that apple, or when you reach the core, is it still an apple? Crisp sets force a hard distinction there. A fuzzy relation, on the other hand, allows for a smooth transition in between. It maps to a continuous interval between 0 and 1, represented mathematically by a 2D membership function. And this is where it gets super interesting. These fuzzy relations let us map highly subjective, real-world human experiences that classical logic just completely breaks down on. Because, let's be real, we don't naturally think in absolute ones and zeros. We think in terms like, well, x is close to y, or x and y kind of look alike, or if the reading is large, turn the dial just a little bit. Fuzzy logic is so much more natural, and technically it's way more expressive because it allows one single mathematical rule to replace dozens of rigid conventional rules. Section 3. Operating on fuzzy relations. Next up in our assembly phase, we need to establish the specific set-theoretic mathematical operations that actually let these fuzzy relations interact with each other. Let's map out our tools. Keep in mind, we're dealing with values between 0 and 1 now. If we want to combine relations to see how much an element belongs to either set, which is a union, we take the maximum value between them. If we want the intersection, to see how much it belongs to both, we take the minimum value. To find the complement, or how much an element is excluded, we simply subtract its membership value from 1. And the inverse, that just reverses the order of our variables from xy to yx. These 4 actions are essentially the hammer and nails of fuzzy mathematics. Let's head into Section 4, the art of composition. This is where we see how all this builds into the core mechanism of our entire system. Here's the big challenge. If you have a relation mapping domain X to domain Y, and another relation mapping domain Y to domain Z, how on earth do we compose a totally new relationship that skips the middleman entirely and maps X straight to Z? The answer is composition. Now, the industry standard here is max-min composition. It takes the maximum of the minimum values. It's definitely simpler mathematically, but here's the catch. It literally clips the top off the fuzzy set. You are losing data. The alternative, which is fantastic, is max product composition. Because you're multiplying the values and then selecting the maximum, it preserves the original shape of the fuzzy set. It loses way less information, which makes it an absolute game changer for highly sensitive systems. Finally, Section 5, returning to reality with alpha cuts. We're bringing this explainer full circle with the final polish, taking our subjective, infinitely nuanced, fuzzy data and forcing it back into a rigid reality. Look, we live in a fuzzy world, but at the end of the day, we often need to take crisp actions. A self-driving car's computer eventually has to decide whether to hit the brakes or not, right? It can't sort of hit the brakes. That's a disaster. This is exactly where the alpha cut comes in. An alpha cut converts a fuzzy relation back into an ordinary, crisp relation by setting a very specific threshold known as the alpha value. To put that into perspective, let's say we look at our data and set an alpha cut threshold of 0.5. Any ordered pair in our fuzzy relation that has a membership value of 0.5 or higher instantly snaps to a definitive true, a 1. And everything below 0.5, it becomes a 0. It's literally a mathematical guillotine that slices right through the gray area, turning all that beautiful, nuanced fuzziness back into the strict, actionable reality of ones and zeros. Which brings us to a final, pretty provocative thought to take away from this explainer today. We've built this massive, highly complex mathematical system just to handle the ambiguity of human experience. But if every single fuzzy mathematical relation eventually requires a crisp binary alpha cut to actually make a real-world decision, was the universe actually fuzzy to begin with? Or is fuzziness just a tool humans invented to cope with a lack of precise data? I'm going to let you ponder that one. Thanks for joining me for this explainer, and as always, keep questioning the data.